Well, particulate radiation is one of the type of ionizing radiations, right. So, we talked about this, and what we will do is the order in which we will proceed is we will try to understand how does particulate, right, radiation interact with the material, and then go to electromagnetic and how it interacts, electromagnetic radiation and how it interacts with the material. Okay, in that order we will go. So, when we talked about particulate, recall, of course, these are just proton, neutron, electron are listed here, but you could also have other particulate, for example alpha particle or beta particle. So, you will come across those perhaps when we deal with radioactivity, right, radio tracers, nuclear medicine that we kind of introduced, right. So, we will talk about those when we get there, but for the purposes of this module, where we are interested in understanding predominantly the X-ray, right, X-ray aspects, because we want to do X-ray in projection radiography and X-ray CT. So, our interest is so far on the X-ray part in this module. So, we will restrict ourselves therefore to the particles that are here, more specifically on the electron. Okay. So, to reiterate, we are only concerned with electron. Actually, we saw this, right, in one of the examples yesterday when we wanted to calculate the number of atoms that will be ionized. We already said in an X-ray tube, for example, we have tungsten at the anode, remember. So, we are only concerned with electron accelerated in an X-ray tube here. See, that is the particulate radiation that we will use. And how is it used? It is used for generating X-rays, right. And so, this is in an X-ray tube generates X-ray. So, we are using a particulate radiation, particulate ionizing radiation to generate X-ray. So, we will see what happens, why X-ray comes out. So, in this context, an electron is accelerated across a tube, and that is why it has energy. So, electron is a particle and it has energy which is sufficient to cause ionization. So, it is a particulate ionization radiation. So, now let us move on. Okay, if I have a particulate with enough energy, how does it interact with the medium, right? How does it interact with the material? So, there are two primary interactions of interest. Okay. First one is very common, right, which is called as collisional transfer. The name is kind of suggestive. What is collisional? So, if I have just to appreciate the concept, I am going to use, this is not realistic, we are not electrons, right, we do not have that much energy, but pretend I have energy, I am the magnified version of an electron, and I am going to with all the energy run through, and there are lot of people, right, lot of other electrons, they are there. What will happen? First thing is I will collide with them, right. I have more energy than them because I am running, right. I have more kinetic energy. So, they are all standing there, I am going to collide with them. What will happen? Most likely, I will probably push them by the impact, they will probably move around. I will lose energy by this collision, right, and then eventually I will lose energy, and all of them, they are now excited, right. I push them, I transfer some energy. So, they have to come back to their rest state. So, in the process what will happen? They will dissipate energy, come back to ground state. So, there is a lot of friction, there will be heat generation. So, all the energy that I carried with me, when I collide, I kind of distribute it, and when they come back to rest, essentially there is a lot of heat dissipation. So, this is the most common interaction that happens. So, if I have a charged electron, essentially it creates heat because it hits the cloud and loses energy. Is this interesting to us? Is this important to us? What do you think? Right? So, we say that if you have a charged electron, right, you give sufficient energy, it will go interact in this manner, and this is the most common interaction. Is this, in your mind, do you think it is a useful interaction, or not so useful interaction. Well, useless or useful depends on the context. What is our context? We want to generate X-rays. What is generated? Oh, it produces heat. That means your X-ray tube, right, is going to get heated up. That's all, right? So it's not really useful for our purpose. What is our purpose? I want X-ray energy to come out, right? I don't want heat energy to come out. So it's common, but it is going to take place. There is going to be heating. So when you design a tube, you'll have to make sure that you have mechanisms so that there is no overheating and stuff. So we'll come to that when we do the instrumentation. Okay, so what could be the other so clearly this is most common, but it's not really that useful for us. What is going to be useful for us? For us, we need to produce X-rays or energy that comes out with X-ray range, right? So that is going to happen due to radiative transfer. This is the one that produces X-ray. Of course, even there, that radiative transfer, there are two kind of mechanisms or two phenomena through which X-rays are generated, right? One is going to be the characteristic radiation, right, where we kind of talked about this even in the intro, right? So essentially, when you knock out the electron in the K shell, remember the organization structure of an atom, that's where we probably mentioned this, and we talked about ionization in the previous lectures. So that there's where we said, you knock an electron and it becomes ions. So this is a radiation, ionizing radiation, so it all makes sense, right? So characteristic radiation is a phenomenon where when you have an energetic electron that goes and collides, right, you have radiate into a material, you have an electron cloud, you have radiative transfer, and the collision with K shell produces characteristic radiation. We will go into that in the subsequently. The other most useful interaction is Bremsstrahlung radiation, right? Bremsstrahlung radiation, what happens here? We are talking about K shell, that is electrons. So when a charged electrons, right, when a high energy electron goes, interacts with the electron cloud, you have something here. Then there is a nucleus, right? So this one essentially has to do with when the charged energetic electron particulate that goes and interacts with the nucleus. That time energy is released, and that turns out to be in the X-ray energy level, and this is more common than characteristic radiation. So from an X-ray tube, for example, it's actually the Bremsstrahlung radiation that gives us the energy mostly. Okay, so we will go look into each of this in the subsequent 20-30 minutes. Okay, so here is a sketch. We will basically start with the first one, right, which is collisional transfer, and then move on to characteristic and Bremsstrahlung. So collisional transfer, what happens in collisional transfer, right? Let me just show the corresponding sketch. Very intuitive, right? I gave you an analogy of me running, and similar, you pretend that's an electron. The electron has energy now, it is going, and this is an atom's cloud, right? You have an atom, you have electron cloud around it, you have a nucleus and electron that compose the atom. So what could happen? First thing is, like I said, you go in, you start to interact, right, lose some energy, and with reduced energy you go further, interact here, with reduced energy you go further, you interact here. So in each process you lose energy, and whenever this comes back, right, when the rearrangement takes place here, it essentially gives you heat energy. So it's small energy that comes in the infrared radiation range, and so that happens. So that is clear. So it is only collisional. It doesn't really knock another electron out or anything like that. It just loses energy, but it still has enough energy to go to interact with the next atom, electron cloud of the next atom, loses energy there, and subsequently until it has energy it will do interact and then die out. So what about this guy? This is an interesting secondary effect. So, you have this electron goes, if it turns out that it can knock another electron, right, if it can knock that electron and give it sufficient energy, it's like, so I was running, several of you, right, in our analogy. So, when I go, yeah, if I try to push through the crowd, people will realign, I will lose energy, there will be a lot of friction, heat. But then it could also happen that maybe I latch on to someone and I transfer a lot more energy, which is sufficient for that person to actually start to go further down and push other people, right. That is exactly what is happening here. So, the charged electron goes, knocks out, it transfers a lot of energy to that, right, to that particular electron. Notice it is on the outer, right. So, the energy as you go away from the center, the binding energy is also going to be less. Okay. So, it is going to knock out this guy and that is going to have sufficient energy. So, now that is an electron with enough energy to go. So, essentially that is another particulate, right, that can go and do the interaction. It is exactly analogous to you have the particulate radiation coming and interacting with this atom. Delta ray is nothing but if this electron is knocked out. So, this is a secondary. So, this is exactly same as what would happen. So, the same interaction of this will now can undergo colloidal or another delta, right, depending on the energies involved, another delta and then so on and so forth. But essentially the idea is even here that is going to be mostly colloidal. So, nothing much happens, only heat is generated here. So, the energetic electron collides with an atom in the target. So, only a small fraction of the energy is transferred. Okay. So, if that is the case, it is transferred to another electron. So, it is going to locally readjust itself and then come back to ground state, giving that extra energy out, right. So, as the affected atom returns to its original state, small energy comes. I mean, when I say small, what do I mean? I mean, it gives out energy, but that energy is in the infrared radiation. So, heat is generated. Okay. So, if you actually recall, it won't be a bad idea to look through our first electromagnetic radiation spectrum that was shown, right. There was a lambda scale, there was a frequency scale, there was an energy scale. We will actually end up referring to that a lot in this lecture and the next lecture. And the reason, so it might be handy if you want to just pull that out and have it ready. So, you will notice that infrared spectrum, the energy is less compared to your X-ray, soft X-ray, hard X-ray, gamma rays, right. We had, and then on the lower side you had microwave, RF and so on and so forth. So, yeah, so there is a energy that is coming out that happens to be in the infrared range. So, heat is generated. Occasionally, like I said, you could have enough energy, right, large fraction of the incident energy is transferred to another electron and that is freed, and now you can pretend that this delta ray is going to behave like all the process we talked about. It is going to do colloidal and radiative further down. Clear? Okay. So, the incident electron's path may be redirected and subsequent interaction. So, it is kind of uncontrolled, right. So, you go in and then lot of atoms are there and this is going to happen. So, this is going to continue. Okay. So, what we are interested here is understand that we are talking about energized particulate that is interacting with the atom. So, it can produce in this way essentially heat. So, this is of not that from a signal point of view, this is not going to contribute to our signal. Okay. Fine. So, let us move on to the more interesting stuff, because we want to produce X-rays. First is the characteristic X-ray. What do we mean by characteristic X-ray? Oh, remember the electron goes, knocks out a K shell, right. Let us see here. So, the electron, this has energy, it goes, but it has enough energy. What is that enough energy here? Recall our binding energy concept, right. So, this has to have energy that is greater than the binding energy of the K shell electron of this atom. If it has energy greater than the binding energy, then it will release this electron. See, that is why we talked about ionization, right. So, this is going to eject this electron out. So, subsequently what will happen? If this is ejected, rearrangement is going to take place. Recall how we talked about excitation, ionization, right. So, rearrangement is going to take place. So, the electrons from outer shell will start to fill in the void and rearrange itself. In the process, the extra energy comes out. How does the extra energy come out? It comes out in the form of electromagnetic radiation. We will define electromagnetic radiation subsequently after we finish particulate interaction, but you would have heard about electromagnetic radiation already. Whatever comes to your mind, right, about electromagnetic radiation, remember the spectra that we showed, that is sufficient at this point. Okay. So, energy comes out as a electromagnetic radiation in the energy is in the X-ray range. So, that is X radiation. We still have to understand why it is characteristic. What do you think? Why is it characteristic? Well, I have energy that I know I am putting in, let us say, right. If I know what is the energy coming out, can I then say anything about the atom or the material, right. In other words, if this energy that you are getting is unique to a particular transition that is taking place for a particular atom. So, from this energy, oh, you tell me you are observing 576 kilo electron volt, then I will tell you that that atom is tungsten, right. If you can do that, then that is characteristic. So, the X-ray that is coming out at the energy levels, because X-ray energy is wide range. So, from the energy of the X-ray, if you can tell what probably is the atom that is involved in ionization that has given out this X-ray, then that is characteristic X-ray. Okay. So, we will spend one more slide on that. So, the incident electron collides with K shell electron. We talked about this, exciting or ionizing the atom, leaving a hole in that shell. So, the K electron shell is having a hole. Then rearrangement takes place. As the atom returns to its ground state, the K shell hole is filled. When it is filling, high energy to ground state, low energy, that means it has to shed out the extra energy. So, that loss of energy creates an electromagnetic photon, okay, known as the characteristic X-ray. So, now this is the deal, right. The energy of the photon, what is the energy of the photon that is going to come? Because it is transitioning, right, high energy to low energy. So, there is a realignment that is taking place. So, it has to be the difference between the energy of the two shells, right, because it is transitioning. So, the energy that is coming out, I know the binding energy of K electron of the atom, I know the binding energy of a L atom, I know the binding energy of M electron, M shell, right. For a given atom, if I know the binding energies at respective shells, then perhaps if I know the energy that is coming out, and that happens to be a difference between energy of two shells. So, in other words, it is actually element dependent. Then I can identify that element, right, from the energy. So, it is characteristic of that atom. It is characteristic of this two shells that are involved in rearrangement. That is why it is characteristic X-ray. Clear? But one another point that you may want to recognize here is, that means I am going to get energies, right, discrete energies, discrete energy level. So, energy comes out at a particular energy level, that is a key. Okay. So, because of that I may be able to tell what two shells are involved and therefore what atom it is. So, it is discrete in nature. Okay. So, what is the other one? So, before we go, just to extra material for you to appreciate the conventions, right. So, caused by removal of inner shell of the electrons and subsequent filling of the holes. Okay, this is what we just saw. So, there are some conventions, because we said characteristics X-ray, right, and you know which shell is transitioning. So, there are conventions for naming this. So, the shell energy difference determines the energy of the characteristic. So, how do we communicate this? How do we be more specific about it? Here. So, you have different shells K, L, M, right. You have a hole and there is a transition that is taking place to fill the hole, and in the process electromagnetic energy comes out in the X radiation. Okay. Again we'll see this again. Electromagnetic radiation, when the energy comes out as photons, the energy is h mu. We'll define that. Okay. So, the point is this comes out. So, now the question is, if this is characteristic, there could be jump from L to K or M to K or M to L. There are so many jumps because it is going to reorganize itself, rearrange itself. So, is there a better way? And each energy could be characteristic. It could be different depending on the respective binding energies involved. So, is there a better way to communicate this, right? So, what they do is the lines are named. Oh, what is lines? Just as I said, what are these energy levels are discrete, right? So, if you do the spectrum of energy, right, you will have lines only at certain discrete locations. You will have the characteristic X radiation depending on what is the characteristic, right. So, these are what is considered lines. So, it is in the spectrum. Remember, spectral lines. Lines are named after lower shell involved in the process. What is the lower shell? K is the lowest, L, M, N. So, lower shell that is involved in the process, right, that shell will be used. The upper shell involved is denoted by Greek letters. What does that mean? For example, if there is a shell transition is n, delta n is 1 shell transition. You can have that one shell transition anywhere, right? I can have M to L or L to K. Both of this is one shell transition. So, it turns out that if it is one shell, we call it alpha transitions. If it is two shells, we call it beta transitions. But then we use the lower letter, lower shell involved in the process. So, if I want to communicate that some transition happened from L to K, delta n is 1. So, that is a alpha transition. So, whatever is receiving lower shell is K. So, if I want to communicate that, I will say K alpha, right. So, let us see. So, some energy levels. So, that is why I said it is for tungsten, all these are known, right, each shell what could be. So, this is your K, this is your L. If you are transitioning from L to K, you are having one jump, delta n equal to 1, which is alpha transition. So, it is alpha transition and you are using the lower shell involved. So, K. So, K alpha, if you say K alpha, then you know you are transitioning from here to here. If you are doing K beta, that means beta is 2. So, K beta, so that means lower is K, beta is 2. That means this would have come from 2 levels up, right, M to K transition. Likewise, here if you notice, L is the lower energy, lower shell, alpha means 1 transition, L alpha represents M to L transition, L beta represents N to L, and so on and so forth. Now, you understand, that means all this, the energy levels are unique. So, if it is jumping and the energy that comes out is also in the X-ray range, that is a unique energy. So, you can tell whether that X-ray characteristic X-ray is a L alpha or a K alpha, right, you can, or a K beta, you know, based on the energy and the energy that is observed, you can tell, and that is unique to the atom. because each shell, each binding energy of different atoms are different, slightly different, right. So that is why it is characteristic. Okay, good. So this part is done. So let us move on to, okay, this is actually giving you some signal, but still this is not really that helpful. Why? Oh, this is going to just give me one X-ray energy at that particular line, right, that particular frequency. So what is the most important interaction from a signal perspective? It is Bremsstrahlung. Remember what was Bremsstrahlung? I told you that it is going to interact with the nucleus. Let us again do some analogy. I mean, I know these probably are very poor analogies, so be it. I mean, at least it gave me some feeling for what it is, right. So pretend you are the electron with energy. So it's like you are driving a car in the highway, you have a lot of momentum, so you are going at a velocity, you are accelerating, you have reached and you are really moving fast, right, in the freeway. So you have enough energy, but then you notice there is this big advertisement, right, something that attracts you, that is flashing. They are standing here and you are able to see that, and they are flashing here. Say, let us say an attraction is there, right, food promo or some other thing. So you see all colorful things and they are trying to catch the attention of everybody who is driving through that freeway. What is going to happen? You will probably apply brake because it is attracting you. You will apply brake, slow down, probably go towards it to get a closer look at it, right. If you are not completely interested, if you are not completely attracted towards it, all likelihood you will go further. So what is happening? There is a center of attraction, it is trying to pull you there, so you are going fast, it is trying to pull you there, so you are applying brake, you are slowing down, and then you lose energy. So essentially you lose speed, so you lose energy because you are braking, and then you find that it is not attractive enough, that you have not still lost all the energy, and so you detour, right. That is exactly what is happening here. So the electron is going, the positive charge in the nucleus tries to attract this electron, and so it is trying to pull it towards it. In the process, this electron is applying a brake, or it is like braking to slow down, and it changes path, and if it is not completely attracted, it changes direction and goes. So in the process, what is going to happen? Oh, it is applying brake starting here because of this influence, it is continuously applying brake to slow down. So what is going to happen? It is going to reduce in energy. So what is happening to that energy? That energy is going to be sent out. So that energy that it is sending out because of this braking is, if it comes out in the X-ray energy range, that is your Bremsstrahlung X-ray. Why is this Bremsstrahlung? Oh, that is just a German word that means braking. So this is braking radiation in English if you want to look at it. So you relate the analogy why it is braking. Oh, that is why it seems like it is slowing down because of this attraction to the nucleus. The nucleus is slowing down, it is breaking the not breaking into pieces, breaking means applying the brakes, right, braking and slowing down. So that energy that comes out because of the braking, because of the slowing down, because of the influence of the nucleus, that energy comes out as in the X-ray range. So this is a most important thing. This is a continuous, right, you are applying brake, so that means you are releasing energy, right, unlike your characteristic which was shell dependent and therefore there was discrete. This is a continuous range of X-ray energy that is going to come out. Okay. So let us just put it, so as an incident electron approaches the nucleus of an atom, the positive charge of the nucleus, right, that is the attraction here. tries to bend around the nucleus and decelerates. Decelerates means slows it down. So, the picture that you see here kind of represents the meaning, right, captures the meaning nicely. So, the loss of energy leads to Bremsstraw lung. Like I mentioned, important aspect is it is a continuous range. Of course, depends on how much speed is lost, right, how it is lost, but the point is it is over a continuous range. So, you come with some energy, you start to apply brake, you start to lose energy, and the energy that you lose comes out in the X-ray radiation range, and eventually it goes out, it stops, right. So, in a rare case what can happen, like in our example, you go, the attraction is so attractive that you actually stop the car and go in. So, your car is no more, you are no more on the freeway, right, you are not going to go to another place, you are just attracted here completely, you are for lack of better words, just to say, you are annihilated, destroyed, right. So, the idea is, in which case what has happened, you have lot of energy, you came in, you got completely attracted, you lost all the energy, you are stopping there, you lost all the energy. So, all the energy that you carried forward has to be released, emitting a photon. So, occasionally when the incident photon collides with the nucleus, the electron is annihilated. In the process what happens, emitting a photon with an energy equal to the kinetic energy of the incident. So, this could be the highest possible energy that can come out, clear. So, probability wise this is less, occasionally only it can hit. So, mostly it is going to be a continuous wave, continuous scale of energies, and the energies should be less than what it came. Only occasionally when this is completely annihilated, the X-ray that comes out will be of the energy that this particulate carried, okay, the highest possible energy. So, the most important message is Bremsstraw lung radiation, this interaction is the major source of X-ray generation in your X-ray tube, clear. So, we are interested in understanding how X-rays interact with X-ray energy, interact with body, that is what we are going to study. But before that, to generate X-rays, we use the idea of a particulate with energy, how it interacts with the material and generates X-ray, clear. Of course, in the process we could not help, but we also touched upon the energies that are coming out is electromagnetic radiation with X energy, okay. So, we did not still really talk about electromagnetics, which we will do now, but the idea of particulate interaction, I hope you got it. It is important, that interaction or the particulate radiation is important in the context of generating X-rays, okay. So, is that our signal? I mean, from a medical imaging perspective, medical imaging systems perspective, is that our signal? Well, that is the signal at the input level, right. You have to create a source signal. So, you have created the source signal. So, radiation, particulate radiation is useful there. Then we need to understand this electromagnetic radiation in X-ray energy range, right. How does that interact with the material? That is the natural, because that is what is important from an imaging perspective. I generate this X-ray, send it through the body. So, I need to understand how that interacts with atoms in the body, right, naturally. So, that is what we will do. Before we do that, this is a very important plot that you see here. I think it deserves some attention and real appreciation. What you see here, because we will end up using this, because like I said, this is going to be sent into the body. So, this is your signal source, right. This is the signal that is sent into the body. This signal with this characteristic is what is going to be sent into the body. This is output from the X-ray tube, okay. So, this is what is going to go into the body. So, it better spend some time to understand what goes into the body, so that when it comes out, based on what comes out. We have input, we have an output. Can we say something about the medium? Say that is the goal. Can we say something about the medium inside, right? Clear. So what do you see here? Two things stand out. I mean, literally one is standing out, right? The lines that you see. What are these lines? These are the characteristic radiation. Of course, example here is tungsten. So these are the characteristic radiation. What is characteristic radiation? We just saw. This is your X-ray photon energy. So this is the photon energy that comes out in X-ray range. What is the range? There is a huge range that is plotted here. I think you understand what these are. Different plots that you see. Each of them are ending at highest energy here, right? Because this is relative. So highest energy here is 0. Actually there is. So here how do you do that? How do you generate the highest energy? How do you change the energy? Oh, this is just nothing but the voltage, right? Electron is accelerated across a voltage potential. So I do first experiment. I have voltage drop of 20, right? Here I don't see anything. So here 40 whatever, slightly greater than 40, slightly greater than 61, 80, 100, 120. So I run the X-ray tube with different voltage drop. Each time I do the voltage drop, right? For that it goes hits the tungsten and X-ray energy is coming out. And that X-ray energy, the distribution of that energy is what is plotted. So when I hit, when I operated with this whatever about 45 kilovolt potential, when I operated with 45 kilovolt potential, then I get the kinetic energy is 45 kilo electron volt that goes bombards with the tungsten anode. Look at the energies that are coming out. The energies that are coming out continuous. It peaks somewhere and then it drops down. In fact, if you look at it, all of the, so if I next increase the voltage, I get this plot. If I increase the voltage, I get this plot. So all of them have this kind of a hill shape. So it is increasing, right? The energy, the X-ray energy that comes out, that is increasing and then it drops down. Okay, number of X-ray photons in each of the intensities. That's what this plot is. So you have so many, so several interesting aspect can be observed. One is, oh, in this plot for example, I don't see any lines, right? I start to see the lines only when I breach some value here. I start to see 2 lines here. Of course, the amount of that is taller, right? But then it appears at the same level. So when I apply 80 also I get that. When I apply 100 also I get that. 120 also I get that. So what is that? Oh, that is your characteristic radiation at discrete level. So depending on the energy that you supply in relation to the K shell binding energy, right? So if when you applied the 40, whatever 45, it was not sufficient to create characteristic radiation. That's why I don't see any characteristic radiation. So only when I started heating with slightly greater than the K shell binding energy of the tungsten, I start to see characteristic radiations, right? So these are characteristic because from the values you can actually comment, right? Because this will be for tungsten, these are the transitions. So all this can be commented, okay, just by looking at this spectral line. So that is one message. So that is literally standing out. The other thing is, oh yeah, we did know that it was continuous. Bremsstrahlung radiations is continuous. So you had 2 interactions, characteristic X-rays and Bremsstrahlung X-ray, right? So one is continuous, the other is discrete. So this is the interaction that comes out. So what is not that explainable is, okay, when I send high energy, right, to interact, I get more X-ray energy. So more photons with X-ray, higher energy, right? That is fine. So that is why it is But why is it a hill? It starts only from here. This is kilo electron volt, right, energy. So you could have some hundreds of electron volts, right? Why is it not there? Why is it not generating that? Well, it turns out that it does generate, but then you are looking at a material which is tungsten, right? So when you have low intensity, low energy X-rays, right, the soft X-ray range for example, or even here if you see, it is sloping out. It is not like, oh, it is generating and then it comes down. What happens to this? It is not generating these intensities. Why? Right? There is no value, no matter how large you apply. Why? Because these energies that are generated, right, the X-ray energy that is generated because of these interactions are small enough that it essentially interacts with the tungsten again, right, before coming out of the material, and it gets absorbed in the tungsten. So it just heats up. Remember, colloidal. So essentially the low energy that is generated, low energy X-rays that are generated and also absorbed by the material, and therefore it does not come out. So it has to have some energy before it can start to come out, have characteristic, and so when that energy is greater than characteristic energy, you get characteristic radiation. K shell electron binding energy, you get characteristic radiation. Otherwise, you get this shape. So you can see that if I want to increase the X-ray intensity, right, I can, so this peak, this peak, this peak, this peak, this peak, it seems like it's linear. So I can increase the voltage and therefore I can increase the X-ray intensity that is coming out. Okay. Of course, why is this sloping down and coming to 0? When does it come to 0? That means I have applied 120 kilo electron volt. If I want everything to be 120 kilo electron volt to come out, that means, oh, your Brahmstra lung, remember, occasionally it gets annihilated. Only then you get all the energy that goes in comes out. But statistically that is very less, right? And therefore when I do 120 kilo electron volt, I don't see the highest energy anywhere, because relatively that is very weak. So predominantly what happens is, you get, when you apply 80 kilo electron volt, you get most intensities you get is much lower than the highest. There are some, and literally negligible or 0 is your complete annihilation. Okay. So this is a very important aspect, because when I do the X-ray tube and I say we are sending X-ray energy into the body, you know, you are not just sending one or the other, you are sending a spectrum inside. Remember that, we will come back to that. Okay. So now we should probably make it little more formal, because we started using the term with the assumption that you would have definitely heard about this before. So here it is kind of just making it formal. So what is electromagnetic radiation? So you have electrical and magnetical wave, right? So both the electric and magnetic waves are perpendicular to each other and they travel perpendicular. So you know, the typical electromagnetic wave introduction chapters in your textbooks, you will see they will use I mean, at least that is what I remember from my course, right? So you have a wall and a floor. So there will be sinusoids, right, depicting one wave, electrical wave for example on the floor, on the wall, and magnetic wave on the floor, and the direction perpendicular to this plane will be the direction of propagation of the electromagnetic wave. Okay. So electromagnetic comprises of electric wave and magnetic wave travelling at right angles to each other. So we will quickly run through typical electromagnetic waves that we actually have started talking. In fact, the first spectrum that I showed will be useful. You just have that picture and you will recall. So we have non-ionizing, the low energy sides. When we talk about ionizing, remember we are talking about ionizing human body. Okay. So in that context, non-ionizing are radio waves, microwaves, infrared, visible and ultraviolet. Ultraviolet, when you push to the limits, still we'll have to be careful, but still it depends on, it's considered non-ionizing until here. Okay. What are ionizing? Then starts ionizing. That is, you have energy levels that are greater than 13.6 electron volt binding energy for hydrogen, right? So that it can cause ionization of the hydrogen atom. So ionizing, we started with the X-rays. Of course, we are interested in X-rays and gamma rays. Gamma rays not probably in this module, but when we go to nuclear medicine. So distinction between what we saw already, right, the particulate radiation and the electromagnetics. The electromagnetic radiation has no rest mass and no charge. So we talked about the electron negative charge, and we talked about m0 and m, talking about relative velocity and therefore relativistic mass. That is not applicable here. Although electromagnetic wave can display both behaviors, that is, it can either act as particle or wave. Okay. So typically when we talk about particle, you can think about, right, what particle? I mean, it is basically discrete packets of energy or photons, right? Energy of a photon of an electron. So when we talk about particle nature, we are talking about discrete packets of energy, which we call it photons. And we talk about energy of photon, you get the, we saw it in one of the sketch before, the energy comes out as h mu. What is this h? What is this mu? Mu is the frequency, h is your Planck's constant. Okay. So h is your Planck's constant. So if to characterize the particle nature, when we talk about the energies, h mu tells everything. Okay, which is what we will discuss further, because extra photons come out with an energy. So that is what we meant. So when you talk about waves, typically how do you characterize a wave? Oh, you have to, wave means you have to have some wave velocity, some wavelength, some frequency, right? So that is your binding equation. So if it's a wave, if you have to describe a wave, you need to know this relation between wavelength, velocity and frequency. So whichever way you remember, that's fine. This is the way to characterize the wave nature, or to describe the wave nature. This will be the parameters that will be used. Clear? So let us stop here. What I would like to do is continue further with interactions of this electromagnetic wave with the material. Thanks.